So this is the truly definition of the time defined for every. So the keywords over here is every value of the time in R. So meaning the real value will be t, as long as the real is actually the t, will be possible to put any t by the real number. Okay. So the function of a continuous value t by t is f. F is function no matter what. Either you put xt, yt, or yeah. So they take on values in the continuous interval ft. So this is actually okay. So from here until here, so this is the value of the continuous interval for the ft itself. On the other hand, for the discrete, okay, discrete, only at the discrete value of time. So okay, so the keywords here, this, but the same time. So discrete meaning, even though we have this kind of things, but the other way around, we put it discretely. Meaning the amplitude is plotted by what they call it, our spacing for the normal layman vocabulary, this one. But in the other way around, in the digital signal processing point of view, we call it interval, the space that between dot to dot. Okay. So yeah. So again, the interval is basically can be various sampling of the analog signal. So meaning the sampling analog signal is how we change the signal from here to be here by a specific interval. So the, as I mentioned earlier, so this one is a sampling interval by the period t. So meaning t is actually the line between the dots. So this is probably in time domain. So say that this it's time domain, and this would be the frequency domain. So maybe this is f, this is xt. So the interval this and this is called t, and the interval this, maybe this is known as fs, the line between those components. Later on we will discuss. Maybe it's not look like this, but another view of illustration. So they call it a sampling rate, and etc. etc. So that would be the idea of discrete time signal. Okay. So the digital signals, the one that I mentioned earlier, discrete time and discrete value. So this, be careful about this one. Discrete and digital, this one. So discrete time and discrete value. Okay, the thing, the what is happening behind the scene is we have this is time, and this is also time, and this is also time, right? Okay. So a sampling and quantization is basically happen. This one is sampling, and this one is quantized. Sampling is just simple, whereby we put it this way, like we cut it into the interval that we discussed before. Quantization is actually the act whereby we put, let's say we have 2.5 to 3.6, 3.5, 2.2. Okay, so we pull the line to 2.5, 3, 4. Okay, so in other way around, 3.5 means right here, right? Okay, that would be okay. However, if say that the quantization is they have the threshold. I mean 3.6. When we talk about this 3.6, basically we will point out this value quantized to be as 3.5. It's not 3.6 anymore. So that's the reason why we lose some dots over here. We can, as you can see here, right? So the same goes to the 2.2. This one is 2.5, right? One dot over here. 2.2 meaning, let's say this one is 2.25 for by default 2.2 is jumping down here. So meaning this value is, after the quantization, will be 2.0 and not 2.2 anymore. So that would be quantization. So the idea of quantization is actually to reduce the what we mentioned earlier in slide number 2, if I'm not mistaken. No, 3. The keyword of manipulated. Okay, so we manipulate the signal, but the signal is the same, pulling from the states of continuous, sampling, and quantize. And okay, right. So everything about signal was done, and next one is the system. So because we have signal, system, and this DSP. So the signal is easy, I think. The next one is the system, entity that process a set of signal. So the things that processes the signal. So meaning we just assume that a system is a kind of box in the diagram. So anything given to the box will be processed and introduce a new signal as the output. Okay, so that will be a signal. So entity manipulates one or more signal to accomplish a function, yield a new signal. So this is a new signal. So this is the system that what we call as a function of H right now. Okay. And then one. So give it. Okay, like we discussed earlier, we have the a paper cup and a rope connecting to the cup. So this is in and this is out. So that would be the things happen in the system. Okay, example. Okay, this one, more or less in our DSP subject, the system is closely related to what we call it, this one. Okay, so maybe in chapter 4 or 5, we will be discussing on this seriously and went to the transform, Fourier, discrete, DT, FT, and so on and so forth. And finally, you can sketch by your own the filter system. So the filter is actually perform operation of the signal to filter out the noise. So the main target of the system is basically to filter out the interference, or what we call it, noise. Okay, to reduce the noise corrupting the desired signal. So example that we have, okay, so the easy things that we can, okay, so if you notice that all the cell phone has a mic right down there. So normally, lately, I guess, at least a phone has a 2. This one is a secondary mic for what they call it, noise cancelling. So some of those manufacturers has even 3, if I'm mistaken. So they are pulling the, and even the, what they call it, wireless earphone, TWS. Okay, I think some of you familiar with the words, through wireless. The thing is, the earbuds, even though they have this mic at the bottom, so they might have the mic also beside here, I guess, because they need to detect. This one is for the external one, so noise cancelling, and this one is for pulling out the voice from the owner of the true wireless earphone system. So that will be the things. Operation signal processing is actually to reduce the core idea of the DSP is actually reduce noise interference correctly. Okay. Okay. Analog versus digital. So yeah, analog should be digital, and when you start to use continuous, you need to differentiate it with the discrete. So this is the anonym of the continuous and discrete, and this one is analog versus digital. So don't tell the audience like, okay, we are using the continuous time frequency, but we use the digital at the same time. It's not like that, but we use both continuous and discrete. It's not mixed around the terminology of the signal. So when you use continuous, opposite of the continuous is discrete, not the digital. Okay, this one is analog. Yeah, we did discuss about the previous one, with the previous slide, as in circuit theory, and this one also, I guess, in logic circuit, right? This one. So pulling the inputs, 8 of input of ANDs, gates. So we have 4 outputs, so etc. So we have the logic circuit and digital system. So we have that one, and the digital signal processing. Okay, includes the math. So yeah, the reason why I started today to use the pen is actually for this keyword, and this, and this. And this technique is either like you can differentiate between two, let's say DTFT, DFT, and yeah, between DFS. This is discrete time. This is the discrete Fourier series, and this is discrete. This is transform. So that would be called a technique. And we have also signal flow graph. Okay. So representation of the signal by sequence of numbers and symbol and processing of this sequence. So representation of the signal. So whereby that would be the ideas of having the digital one. Mathematically and algorithm. Oh, okay. The one that I said earlier here, mathematically and technically. So whereby we need to deal with algorithm manipulation of a discrete and quantized. So we've been discussing about the discrete and quantized, right, just now. So be careful about this. And this one is the natural digital signal. So S N N. This one is X T converted to XN. So this one is XN converted to D. Maybe another FN. Okay. So the digital representation of the signal and use digital processor. Okay, this one is, I think, related to this one, SFG. Okay, how to extract information and modify. Let's say you are given such a design of a flow. Let's say this will be go like this, maybe feedback like this, and go and this. So maybe you need to check this signal flow graph, either is good design or not. If not, then you should suggest a good one. So maybe, I'm not sure. Okay, so the DSP itself, it's digital signal processing, refer to processing of digitals using digital technology. So this we mentioned earlier, signal, system, process. So this one is input, system, output signal. Input signal, system, output signal. So we have signal to be processed, the DSP system, and process signal. So this is normally a terminology of signal. A function physically contains a set of independent variables, information, etc., etc., etc. So we can have an image. We have JPEG. We have MP4. We have V over here. And extract of any that takes any input, operates, and produces the outputs. So this one is the system. So just now we put it as HT, right? The system. By processing, we mean the operating in a fashion of a signal to extract some useful information. Meaning, let's say this is a signal plus noise, right? So at the end of the day, this signal will be filtered by a system with a smooth, beautiful signal. So that would be the targets of the DSP, removing such unnecessary components by setting the filter design. Okay, spec. And okay, so why DSP? The why process signals? Signals are corrupted by interference. Means the one that we discussed just now. Say that we are Say that we are in the outdoor situation. So basically, signal example, especially the signal, the voice signal has been corrupted. So we need to filter it out, and so that will be pulling out the interference due to the noise. Signal are distorted due to transmission medium, maybe, okay, so this is A, this is transmission. So during the transmission from this point to this point, let's say we have this signal. So maybe the signal which has been transmitted from A to B is not slightly 100% the same due to the transmission medium. So yeah, so this, I'm not sure about, speaking of a fiber, maybe this statement is valid for during 10 years back, I guess, before the fiber optic came in. Recover information present in the signal. So this is actually what the DSP do. So have a, take the signal, filter it out, and give the good signal to the user, and perform algorithms such as modulation, compression, etc. Okay, so that's one is modulasi. So normally, say that you have been asked about what is the components of the system. So this might be a good idea to refer. So we have analog inputs, analog outputs over there. So analog filter input, and this one, the one that I mentioned earlier in this. So slide 10, we have continuous. This one is what they call it, sample, and this one is quantized, right? So this is actually this step. So once we convert it to analog to digital, so because we want to have this signal from analog to digital, we need to use ADC, right? Analog, okay, over here, digital converter. So, and then this will be go to the DSP. Okay, then, so if this is slightly can be debatable here. Could be this one is user A and user B, or user A, or this one is before the transmission. It could be possible. So once the information has been sent to the another user, as example, so this one will be converted again, right? So DAC, meaning the received signal from the transmission point center, a pure signal from the digital will be converted again to the analog, and the DAC will be play the rules, and at the end of the day, example, as a cell phone, so we can hear the voice of our parents say Assalamualaikum ma, and so on and so forth. That would be the analog, not the digital one. Okay, so whereby during this transmission is actually in the digital, not in the analog. So that would be, I just put it a line over here to separate it to the different world, to different user, meaning this one is A or this one is B or something. So we have the components of a DSP system. So we have, okay, this one is actually the one that happened in those boxes over here. So this one is analog input. So output of the sample and hold will be here, the second one. So ADC and DAC, this one is the binary sending to the user. I think this one is the transmission. So while received to the receiver side, it will be DAC back, and this one is as a voice back. So this one is a voice. So this one is in binary or something, or digital. Okay. Okay, for the DSP operation example, I think, yeah, that would be mini, signal correlation, digital filtering. So the one that might happen always in our subject will be this one, filtering. Modulation, demodulation. Okay, this one is vice versa process. Transmission. So, okay, that's this. Okay.
Okay, thank you guys for watching NMZH channel. Hopefully you can get knowledge and benefit from the videos. Thank you so much. Assalamualaikum.